Okay, so how would one go about actually doing non-equilibrium physics in the expanding universe? Just remind ourselves the terms that we've used so far, right? So we have these two fundamental equations. In order to solve the Friedmann equation and the energy conservation equation, we need normal thermodynamic quantities like energy density and pressure. So these are, if you want, macroscopic classical physics quantities. But really, in order to do non-equilibrium physics, it's more useful to look at microscopic quantities. So we call this the macro world. But really, on a micro level, what is it that we're after? Well, I mean, of course, if you want to do the full quantum treatment, then you would need something like, for example, a density matrix in order to do this. But what we'll stick to doing here is something relatively simple. We will use what is known as the one particle distribution function, which is a concept from classical statistical physics, which is more than adequate to what we are going to do here. So of course it would require a more rigorous treatment, but what you can relatively easily show is that our normal universe is actually a very dilute environment and there are no entanglement effects. So you typically have something where you have simple, well-defined free particles moving around, then doing some more or less point-like interaction and moving off again as a plane wave. So in other words, we're always looking at something like the Born approximation in scattering theory. So this one particle distribution function, since we're always talking about free particles, is nothing more than the number of particles that you have in a given phase space volume, dx and dp, at a certain point in time. And of course, you can construct all macroscopic quantities from this one particle distribution function through simple phase space integrals. So for example, right, if you wanted something like the local energy density, you would need at some point in space, you would need to do an integral over momentum space. You would need to sum over all possible momenta of that distribution function, and then you would have to remember that you should weigh this by with the energy associated with that momentum. And then you have to remember that there's a fundamental phase space volume, which is basically h cubed. And since we're working in a coordinate system, right? So this actually is 1 divided by Planck's constant cubed. But since we're working in a unit system where h bar is equal to 1, then you only get the factor of 2 pi here. That's how it is. So this is the energy density integral, and you can do all corresponding macroscopic quantities by similar integrals. I think I showed it in the previous video, for example, that you can get the pressure through exactly the same type of integral by appropriately weighing the distribution function, in this case with p squared divided by 3 times the energy, and so on and so forth. And just like in macroscopic physics, there's a conservation law for energy and momentum. Of course, there's now a conservation law of some sort for this distribution function. And there are also equilibrium forms of the distribution function. So let's maybe start with the equilibrium forms of the distribution function. And what do I even mean with equilibrium? So you know from statistical physics that there are certain different types of equilibrium. Either you can have what is known as full thermal equilibrium, in which you have some box of particles in an isolated system. The total energy is given, but that's all that's given. And then you can allow particles to redistribute both number and individual energies, and they will do that. So the number of particles is not a conserved quantity. So that's fourth equilibrium. And in that case, the distribution function always takes one of two forms. It's 1 divided by E to the E divided by temperature, plus or minus 1, where the plus is for fermions and the minus is for bosons, right? So plus is for spin 1/2 particles and the minus is for, and so on. Where in the standard model, we're always interested in the spin 1/2 and the spin 0 and 1 cases, right? So that's all there is to it. So this is either the Fermi-Dirac or the Bose-Einstein distribution. But you could also be in a case where you have something not quite as equilibrated. And that's very often the case, for example, when I talk in this room, we have a certain number of molecules floating around, and to a very good approximation, that number is a conserved quantity. You cannot just remove particles, right? So, for example, the number of protons and neutrons is a conserved quantity in this room and in most normal circumstances. And therefore, I cannot have full, complete equilibrium. So then I'll be in the case where number is a conserved quantity. So that's, for example, also what you use in a star. And in that case, you can write the distribution function pretty much the same way, except now you need one additional term beyond the temperature, namely what is known as the chemical potential. So you have one additional constraint, namely number, and that leads to one additional parameter that you need in order to describe the system, and that's the chemical potential. So we know, for example, right, that in a neutron star, particles are very non-relativistic. We know that the temperature is extremely low. If the temperature was extremely low and you had number conservation, non-conservation, then this term goes to 0. You have a rest mass term here. This term blows up. F goes to 0, and you have no particles left. And in order to make that not happen, you need the chemical potential. Same thing, of course, with the solid state physics and in many other cases, right? So this chemical potential is often very, very useful. So these are the two types of equilibrium that you would normally also be looking at in cosmology. But of course, you could also be in a case where you have no equilibrium whatsoever. And then the question is, what happens? Then the distribution function presumably is neither one of these, but something else. So that brings us to the formalism that we need in order to understand non-equilibrium physics in an expanding universe. And what we need is some kind of conservation equation for this one particle distribution function. And actually that's surprisingly easy to write down. So in the absence of anything that takes away distribution function or adds distribution function, understood in the way that in the absence of anything that transfers energy and number into whatever particle species you're looking at, or transfers energy and number out of it, we can actually write down a very, very, very simple equation for the conservation of the distribution function. It's just that the time derivative is equal to 0. But that's kind of a trivial and non-meaningful statement, right? So what I actually mean by this is that if you take some little blob of phase space and you move it to somewhere else in phase space so that it appears here at some later time, then the total amount of phase space blob, if you want, fluid in that little volume is a conserved quantity. And that means that the actual derivative I have to do must be what is known in fluid mechanics as the material derivative. You have to actually do the derivative along lines of motion in phase space. So really, I can apply the chain rule, and then what it would look like would be something like this. Since I have 6 phase space variables plus time, the total equation gets to look like this. So this is a conserved quantity. Now, of course, if I have a system, for example, with 0 velocity, then this term dies. This, remember, momentum change with time, that's a force, that's the application of a conservative force to the system. If that is also 0, then these two terms die, and then indeed, yes, I'm back in the situation which is trivial, where I say, okay, the distribution function cannot change because it just sits there statically and it's not subject to any force whatsoever. So what would it do? Nothing. It just remains frozen in time. And in particular, of course, in our case where we have a homogeneous and isotropic universe, that would be super trivial, because then it should just be 0 and there should be nothing more to it. Now, of course, life is not quite so simple, right? We're actually in an expanding universe. I should also say that, and I said it before, I think, that we're now looking at the case where distribution function is a conserved quantity. That means that we have no particles annihilating into the species I'm looking at, and we have no species particles annihilating away from this, so that I cannot take or give stuff to the system of particles. Okay, but in general, of course, this is a super nasty equation to solve. What I can show, and we'll show that later explicitly actually, is that I can actually use this so-called Liouville equation to derive all the normal equations of fluid dynamics, like the continuity equation and the Euler equation, the Navier-Stokes equation, and so on. They are all embedded in here somewhere. And the way they are embedded is that you have to transform this from a microscopic equation to a macroscopic equation. And you do that by integrating over momentum space, just like I showed you for the energy density before. Same thing when you do integrals or moments of this equation, you can actually rederive all the normal fluid mechanics equations. But this is a deeper equation. It has more content than the normal fluid mechanics equations. And we'll see that a little bit later. Now, before that, let's just try and see what happens in a universe where you have the cosmological principle. So if the cosmological principle is obeyed, let's just write down this Liouville equation again. Like this. Then one can start to throw away terms very easily. So for example, this is the gradient of the distribution function, the spatial gradient. But the spatial gradient of the distribution function surely must be 0 at all points, because otherwise you cannot have the same value at all spatial points, right? And then you violate the cosmological principle. So surely this term must be 0. And then naively, perhaps one would think the same thing applies to momentum. But that's not actually true, because momentum, well, you could have, for example, a particle, think of a normal Fermi-Dirac distribution or a Planck distribution, right? So something that looks like this. Take the Planck distribution for photons that looks like this. So clearly that doesn't depend on position in space or direction in space, but it depends on the magnitude of the momentum. So we expect that to be non-zero gradients along the direction of momentum direction. And that means it's actually useful to write out this gradient as not something in Cartesian coordinates, but something in polar coordinates. So then I get this term. So now I write it as a magnitude of momentum gradient here. And then I get, of course, now a direction gradient. So I get a unit vector in momentum space. But this quantity, that must be zero, right? Because the distribution function surely cannot depend on the direction in momentum space, because that would lead to more flow of particles in some particular direction, and that's not allowed. So this must be zero. And that means I'm left actually with only two terms, namely the explicit time derivative here, and then one gradient with respect to magnitude in momentum space. So the full Liouville equation looks like this. Oops. So only one thing now remains, and that is one can actually rewrite this. So remember the geodesic equation that told us how the magnitude of momentum evolves in an expanding universe. And it was super simple. So what we ended up writing the geodesic equation as was this p dot divided by p equal to minus a dot divided by a. That's the one that gives us p equal to 1 divided by a, or proportional to 1 divided by a. But down here I have the p dot term. So I can actually write p dot as minus a dot divided by a times p, or minus the Hubble parameter times momentum. So the final form of the Liouville equation in this homogeneous and isotropic universe is simply this. And perhaps it's a little bit difficult to see what the deeper physical meaning is to this equation. So one can actually go a little bit deeper and in understanding it through, again, momentum integration. So that's the next point on the agenda, that is to actually integrate this over momentum space to see what comes out.